G'day guys, been doing a few tests and just proving out whether swapping those two transistors actually make a small difference or a big difference. Now, I've put in two different types of P-channel MOSFETs and I've put in two different types of N-channel, and some are very low on resistance and with associated higher capacitance, and some have got a higher on resistance with less capacitance. So it has less charge to turn it on and off, and less leakage or greater leakage, and less on resistance. So I was thinking to myself, what is the criteria we're really going for here? And the criteria is we want as low as capacitance as we can get, and we want as low on resistance as we can get. And usually they do not go hand in hand, so there is a trade-off no matter which way you go. So I've got some super very, very small devices. Now, these are probably the best N-channel direct replacements you can get, and I'll tell you what they are, because if you go hunting for them, you won't find them. They're very hard to get your hands on. I'm pretty sure they're made by Vishay, but don't quote me on that. These are an SI1022R, and these are very, very tiny, very, very small MOSFETs. I can't even remember what the case is. It's about the quarter of the size of a SOT 223, so it's very tiny indeed. Anyway, I also have the same one in a P-channel version, and the P-channel one has got very, very low capacitance, but it doesn't have the low on resistance as what the N-channel does. But I did try it anyway, and even with the higher resistance, I did my small gold tests all the same, and it worked better. So it's gone, well, this is very interesting indeed, because the capacitance of the N and the P are very similar. They're very similar indeed, very, very low. They're like something like 30, 25 or something like that. They're very, very small values. And I'm thinking to myself, well, if we've got the other P channels I had in there, which were that, what I mentioned in the other video, the strange number, whatever it was. I've probably put the bag away, have I? Hang on, it is here. Sorry. I put the FET somewhere. Yeah, these RSC 002 P03 T316s. That's the ones that I had the best results with. This on my normal setup where I use, I'll show you the setup. That means I've got to crank this thing up in the air again. But anyway, here we go. I had it set up on the board there for a reason. On that setup there, you can see I've got my two separate coils. I've got my Waco ruler, unfortunate name, if you're from Texas. But yeah, that is set up. I can do some very, very exact measurements with small gold, bigger targets too if need be. But the way it's set up is small coils, anti-phase. The reason is I can run the detector in mono mode, and there is basically no no interference. There's hardly any interference. So then I can concentrate on more like the interference from within the detector itself. So go back down again. I hope you all didn't get car sick, but you know, it's very interesting. Oh, here we go, visitor time. Every time I set up a video, I get visitors. Yeah, there you go. Gone. It's the same two perpetrators. But anyway, so those devices I just mentioned work extremely well. Now, the other thing I did on the N channel high voltage FETs that live on the other side of the board, you know the ones I mean, the 2SK1334s, they are direct driven. The gate of one is connected to the gate of the other, and it goes connects up to the BC857, which is a speed up off device. It's set up because it's a P channel. As soon as you drop drive, it just goes. It wants to basically go from collector to emitter as a low impedance source, so it helps dissipate the gate charge. And I'd take it that's probably the way, or their thought of doing things hard and fast, and you know, turning those N channels on really fast and turning them off really fast as well. I have actually turned the detectors on and just removed that transistor, right? And they work just the same if you ask me. But anyway, might be for a reason. I don't know. Didn't design it. So I've got a different board here at the moment. It's a different job. So yeah, we're stuck with the N channel on the high voltage side, because if we start using high voltage P devices, our signal will just dissipate down the gate channel. It'll just go to nowhere. You'll be lose a lot of signal. I've never done it. I wouldn't do it. I really don't know exactly how much you'd lose because I've never done the experiment, but it would be substantial. You would have a fairly large gate capacitance there, and you'd also wouldn't have a decent enough low on resistance either. It could be somewhere up around 10 ohms or so, where with the ends you can get about 1/2, maybe less than one. If you start hand selecting devices, you'll probably get down to about an ohm. So this is what can be expected. But the only thing we really can play with is the small ones on the secondary ones that go into the MOSFETs. The other thing I found too, I had a look at the not the switching voltage on the BF908, but its constant voltage supply on pin yeah, well, it is actually, I suppose it's pin 1 on the device. That's the top gate connection. And what I did there, I could see that was getting pulled up and down with switching. It shouldn't be, but it was. So what I actually did there, I got a little 0805 or 2112 type 10 microfarad surface mount capacitor, and I put that from pin 1 down to pin 4, which is ground, low level ground, and that got rid of that. I don't know if that's an actual, well, I'll tell you, I don't know if it's actually a good idea to put that on the low noise ground, because if there is anything as a differential type voltage compared to the two grounds, it could couple in on the low noise ground through those devices. But I did it and it got rid of that instantaneous pull down. Then again, I had a look at the switching waveform on pin, what is it? It'll be pin 2, gate 2. I'm not really sure on the pinouts of these. I'm not sure if it goes 1, 2, 3, 4 or 1, 2, 3, 4. I think it goes 1, 2, 3, 4. And I just put them in. I just know what's what. I haven't looked at those for 20 years. So I just know which way they go. Pinouts are secondary to me. But there was ripple on the switching on the positive side, and also by putting that resistor there, that actually smoothed out some of that ripple. Now it's very interesting because it's only around that device, and I've checked around the other devices there, and they're relatively clean. So I don't know why ripple's ending up on the component connected to the same rail as such. It's bizarre. It might be a proximity thing. I have to investigate more. But at the end of the day, after doing all these swaps, changes, observations, and actually doing target tests in a low noise environment with the special coils set up, the difference between the standard N-channel devices there and the very low noise P-channel devices, say on this is small gold targeting, very small gold, and if I remember rightly, it was showing something like 25% fringe distance improvement by changing it to P. Why this is so? The only thing that is anything by doing this is the lower noise. The lower noise of the P-FET. They're all trench FETs. They're all trench channel FETs, and they're very low noise in themselves, but the difference, even the lower on resistance of the N, was blitzed by the lower noise of the P, even though in the scheme of things it's only fractional. It really is, it's fractional. It made a big difference. So I'm just saying that, I'm putting that out there. That's my own observation. Now, unless you did that test, you would not suspect that. That's why I like, it's the old saying, trust but verify. And sometimes you read stuff, and it could be in electronic books that have been around for years and years and years and years, and it will have statements in there, and everyone will parrot the same thing on and on and on again. Yeah, okay, no worries. But you do the test yourself, and you get a different result. So I don't know if it's other componentry around interacting, or what the story is, but it is not textbook as such. There is differences. The other thing, like, it's same if you use simulation software, and you go, okay, well, this should simulate this perfectly, and you build it up, and no, it doesn't work exactly as it said. There will be things that sometimes the simulation software doesn't take into account. So it's always good to build it, test it, observe, and just see if it's the same. But anyway, that's just a fill in on those input devices. The other thing I did as well is, because these things are hardwired, the N channel, the high voltage N channels, for some reason or other, they're set up to be switched off really fast with that BC857 there. So what am I thinking? I'm thinking, okay, it's for a reason. It maybe it stops them blowing up or something. It turns them off very quick. I don't know. Stops anything bouncing around or ringing or whatever. I've never observed anything, but it could exist. It could be there. It might be with a particular type of coil. It might not do it with my coils. It might do it with someone else's. I don't know. There's so many variables. But it's just interesting that on the bottom ones, direct connecting the drive to those FET gates, I'll tell you right now, no matter if it's N or P, there is a loss of signal. There is a loss of signal, right? So what I'm trying to do is I'm putting it, well, you saw in the other video, I put the 2 series resistors in there. So, you know, because they're such a small gate charge anyway, it doesn't really make much difference. But I tried 10 ohms, I had 100 ohms, I tried 330 ohms, and I was just listening for noise, and I was just watching the switching waveform. They switch perfectly anyway. But when I went down back into the direct drive, I lost signal. And the higher the resistor value was, is the more signal was retained, because the signal doesn't want to run down a high value, well, within reason, a high value resistor, and go through the rest of the circuit and get dissipated. It wants to avoid that. So I suggest putting something like 150 ohms to both gates on those devices will bring a benefit, no matter what device is in there. On the 2SK1334 high voltage transistors, to get less crosstalk, if you're going to run cancel mode, and if you want less crosstalk between the devices, you can put in something like 15 ohm. You've got to cut the track and do all this, but you'll put 15 ohms on each gate back to the driver circuit, which is more or less straight out of that ADG 333. I'm just trying to think about that for a minute too. That might have a 100 ohm resistor in series somewhere. I'm just trying to think back. I'd have to go and track it out because I haven't done it for a long time around that device, but it could be. So you want to check on that, and if it has, then you may want to lower that, and then say put 25 ohms in each gate leg. So the values stack up to be the same. It's not going to change the circuit. It's still going to work. But the thing is, you do want to be able to discharge the gates on those really fast, and putting a 15 ohm resistor there or 10 ohm resistor is not really going to be detrimental to the speeds these things switch at. It's not that fast. It will cause a bit of a softer turn off, and you probably couldn't even measure it, but a little bit of a softer turn on. And if you look up gate charge and the time constants and that, it's fast enough. You're not missing anything. It turns on the stabilizers, then it goes into receive after it's stabilized, and then when it stops receiving, it turns off. So there's no glitches or clacks or anything. On my previous experiments of doing that, there can be a benefit, but if you're going to run mono mode, I wouldn't worry about it because everything's coming in identical. It doesn't make any difference. There's no crosstalk, and if it's a crosstalk there, it's exactly the same crosstalk. It's not going to make any difference. So that's that. But anyway, that's one thing I was going to fill you guys in on about you fellows who want to experiment around in that part of the circuit. The other thing was too, on this one here, it was behaving very strange. It was working, but it was unstable. It was just creating noise, and I could hear it. The only way I could hear it was actually with those 2 coils running in counterphase. And what it was, I'm going to have to hold this up to show you exactly what it was. I don't know if you can see. Oops, hang on. It's saying low battery, but that's all right. Please focus. Can you see that one strand? That one strand on that middle pin. That's all that was holding on under the heat shrink. And a lot of other wires, many strands had already broken. So when I pulled the heat shrink back, I was left with this was okay. The big ones are okay. The black wire and the red wire that go here. But these little smaller wires, they'd broken many strands on both the input receive channels. And that was causing noise. I haven't replaced it yet. I'm going to. That's why I've got the wire and that set up here in that box. So if you have a look at the wires, if you want to grab one of these, I mean, if you want to have a look at this, I mean, how work hardened is it? It's just tough. Even the bit with no paint on it, it's really it's really tough. You know, there's no give in it whatsoever. I think you can probably bend it like that. That's how work hardened it is. It'll just stay there. So the copper is hard, and what happens? Vibration. You know, dirt roads, bumpy roads, poor old detectors jigging around like this breaks the strands. It's common. It's well known that the strands break. You know, even the big thick wires, they're hard. They're just hard. Yeah, it's just basically copper is no longer soft. It goes hard and it bends and bounces around and eventually breaks. And look, I would say there's a lot of people with some of these detectors out there running around the goldfields and half their strands are gone and you're not getting as much power into the ground through their coils. They've probably got some issue with the signal coming back. And yeah, it's very common. I've even found some of the wires, even around here, where they come into the board, that if you have a look close to them, that there's strands just not connected, they're just broken up against the solder where they're put into the board, and all that is going to cause inefficiencies. So you should always check this here. You know, you put on heat shrink tubing on each wire. Is that a blessing that it holds the wire more steady, or does it just hide it if the strands break? Because it can do both. So I myself personally, I do not put heat shrink on the wires. And in some cases, what I will do is I'll have the wires come out and maybe half an inch away from here. What I will do, I will just put hot melt glue or something of that nature on each wire to each other, just so it's stable. And yeah, they're all sort of holding each other to stop that vibration on those points. And yeah, I've never had troubles whilst doing that myself, but I do not use heat shrink because a lot of my detectors, my own ones, personal ones, I'm always pulling them apart and trying this and trying that. Like, you know, at any time, there's always something going on with a detector, and you know, it's ready to go out for a field test. So that's what it is. Don't forget, I'm putting up that video of the standard GP ZZ7000 and the modified ZZ7000 tomorrow night. I'm not. The reason I did mention it, the reason I'm not putting it up now is because everyone's taken the Friday, the Saturday, the Sunday, the Monday off as you know a means of getting out and about, extending the Easter holiday a bit. Maybe you know they even take Tuesday off and come back Tuesday night. What's the use of putting up a video if no one's around to watch it, especially your target audience who are detectorists and no one's at home watching anything, or you know they're out in the goldfields. There's no internet, there's nothing. So I think that's quite wise not doing that until we know everyone's home. That's probably a good idea. Otherwise, it's just a waste of time and effort. Because I've noticed once I put the videos up, they get hit hard. You get hundreds of hits and then it just fades off. It's not a big market as such. This technical stuff, it's not a big market for it. You look at anyone's technical channels there. I mean, there's some that are quite entertaining. Mine's just, there's no rehearsal or anything. It's just, it just comes as it is. And thus it could be boring or it could be, all over the shop or whatever. But yeah, most technical stuff, you look at it, it gets 100 hits, 200 hits, and even some of them there could be there for 5 years and they've only had like 200 or 300 hits or views on them. So it's same with this. There isn't that many people interested. The general detectorist is not interested in how their detector works. They are interested in, does it get gold, and that's about it. But the funny thing is they should be interested in this, because then you can keep an eye on your performance of your detector and know if it's working properly or not, and not out there wasting your time, because none of them would know that the wires start breaking. You wouldn't know it. You wouldn't know it at all. You got the transmit. Say a transmit wire started breaking. It was hanging by one strand. Well, you're probably losing 5 to 10% of your power. Depends how long the strand break is and how far up it goes till it connects to the other strands. But even that will create noise. It'll touch and wiggle and wobble and generate noise. So there's all this sort of stuff. Anyway, I think we've got more visitors coming. Yes, we have. And it's going to get noisy because they're all going to be Filipinos. I'm waiting for it. We can hear the... Here we go. Anyway, I'm going to get out of here because Charlie's friends have arrived and it's going to get loud and noisy. I just know it will. Anyway, catch us.